Canonical observation form. So we have a system described by a differential equation with an input u and an output y, and it is a third order system. And I will have to derive a state equation in this exercise. And the first question is to show an integral formulation for this differential equation. My system has the form y dot 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 plus a2y dot dot plus a1y dot plus a0y equal b2u dot dot plus b1u dot plus b0. Now I can write by isolating this term. So I will have y dot 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 equal, so I will have b2u dot dot minus a0y dot dot due to this one plus b1u dot minus a1y dot. So I can understand that first I put the second derivative, then the first derivative, and pu minus a0y. Okay, so here no derivative. Now I will integrate 3 times this equation, and I will get that y equal to the integral of all this expression. D2. So equivalently, the integral I can distribute, and I will get y equal integral a single one only, because I have the two derivative of b2u minus a2y. Okay. Then I will have another integral, and inside I will have b1u minus a1y, and plus a last integral b0u minus a0y. Okay, so now I have not any more derivatives, but I can understand that in the 3 integral, due to the fact that I have 2 derivatives here, it remains only 1 integral, and when I have 0 derivative, then this quantity will be integrated 1, 2, 3 times. Okay, so now I will call this quantity x dot 1, or equivalently this quantity is called x1. This quantity between bracket, I will call it x dot 2, and between accolades I will call it x dot 3. And from this I will be able to write x1 is equal to the integral of p0u plus a0y, x2 equal to the integral between b1u minus a1y plus x1 and x3 equal to the integral between b2u minus a2y plus x2. So all these equations come from this. From these three equations, I can get the block diagram I will now show. So I will draw my integrators. First integrator for x1, one integrator for x2, and one for x3. Here I will have x dot 1, and I know from this equation that I can, from this equation, I know that this corresponds to x dot 1. Here I have u. Here I have y. And this equation tells me that x dot 1 corresponds to p0u. I put a header here, minus a0, excuse me, here I have a minus, y. Now I will wire the second equation, which corresponds to x dot 2, given here. So I will have p1 u. I put a header here. I will have minus a1 y, so or x3, and here plus x3. For the last one, I will have here this quantity, b2, here adder, minus a2 due to this, y. So this wire corresponds to a realization of the differential equation previously shown. Okay, so I answer the question number 2. Now I have to give the corresponding state equation. So I consider this one. Question number 3. I will write x dot 1, x dot 2, x dot 3 under the form of the matrix A multiplied by x1, x2, x3 plus b plus the matrix B times u. Okay, so x dot 1 corresponds to b0u, so b0u plus minus a0 y, but y corresponds to x3. This is why here I have 0, 0 minus a0. For x dot 2, I will have p1u plus x1, so plus x1, and here minus a1 due to this. 0 here. For the last one, x dot 3, I obtain that I have b2u and 0, 1 minus a2 due to this. And for the last, I have y equal, so it corresponds to x3, so I will have 0, 0, 1 times x1, x2, x3. So I was able, from J of S, to get a state equation which is a specific form, which is called a canonical observation form. Last question, I have to compare the canonical observation form with the previous exercise with both the canonical control form. So I have represented here the two representation. Here the canonical control form, and here observation form. And I will compare them. First, I can see that I have the same structure in terms of chain, and on the wire I can see that I replace, for instance, the second one, y by u by y. If I inverse all rows like this, if I represent here all other, I represent by a join like this, and if I represent all joins by a adder, oops, that's a join, sorry. Then from the observation form I get the control form, and reciprocally. Now from the structure of the state representation, I can see that this matrix is the transpose of this one. Then this matrix corresponds to this one transpose, and this matrix corresponds to this one transpose. So I can see here that I have a duality between the two representations. One is called control because U goes directly to the chain, so I can control it directly. And this one, so I have to remove, of course, I have to put Y here and U here. So I take the previous representation like this. So it is called an observation form because all integrator goes directly to Y, the observation. Both are also equivalent. It means, so how can I prove it? It suffices that to notice that if I take the transfer function of the two of them, which is given by C S I minus A B plus D, but in our case there is no D, in this situation, we of course get the same transfer function. So just a remark, if I have a system S given by a matrix A, B, C, and D in general, and if I make the new system X prime given by A prime, B prime, C prime, D prime, but with A prime equal to A transpose, this one by C transpose, this one by B transpose, and this one by D transpose. So S prime is made from S by some transposition, that I get the same transfer matrix in case that I have one input, one output, and it's quite easy to check, and it is exactly the case we have here. So here is some kind of generalization to show that this transformation can be done for all systems. So how can I prove it? I take S prime and I will compute G prime, the transfer function for it. So I will obtain that it is equal to C prime times SE minus A prime minus 1 B prime plus D prime, which is equal, due to the fact that are linked by some transposition to the matrices of S, I will obtain B transpose times SI minus A transpose minus 1 C transpose plus D transpose. Now this is equal to B transpose times SI minus A minus 1 transpose, because I can permute it, the transpose and minus 1 C transpose plus D transpose. So here I have only permuted the transposition with the minus 1 here. This is equal, so since when I have a product of two matrices, if I transpose them, then I have also to permute the matrices. This is why here I will factorize the transpose and get C SE minus 1 B all transpose. So I have factorized the transpose and I have to permute the matrices plus D transpose. So now I will have only one single transpose by saying that C SE minus 1 B plus D and only a single transpose. Now, since this corresponds to J of S, where J is the transfer matrix associated to S. So I have G prime of S is equal of G of S transpose. That's what I have proved here. Now, since J of S is a transfer function, because the dimension of U is equal to 1, the dimension of Y is equal to 1, J of S is not a matrix, but it is a scalar. As a consequence, it is G of S transpose is equal to G of S. A scalar is equal to its transpose. So I can remove this. As a consequence, the transformation I have shown here will transform one system into another by some transposition.